Okay, so for today's lecture, I want to pick up where we last left off on our crash course of C and kind of complete out some of the readings you might have in the essential C PDF that you have, and kind of provide some tangible, real example code so that as you read more in depth about some of the concepts that drive C and some of the pitfalls and some of the ways that you can go ahead and implement your code, you can actually see how to do that in person or in practice. And so I'm going to pivot a little bit. I've been using VS Code and I've been using Finder previously to be able to go ahead and open up my files and to be able to view my source code folders. But this is a systems programming class. So why don't I use my terminal to be able to illustrate that it's fully equipped with all of the applications that I need in order to accomplish my task. So for instance, for today's lecture, I'll be using Vim for viewing my source code files. I'll be using the LS application to be able to inspect over here all of my files that I want to go through. And of course, we've already been using the command line to go ahead and use the GCC compiler. So I'm going to use three different command utilities or shell utilities to be able to do everything I need to do without having to use really a windowed application. Okay, so I want to pick up where with this concept of pointers, and I want to bind our concept with pointers to that of arrays. So that's where I want to pick up on today's lecture, and then we'll move on and talk more about some strings, functions. We'll take a look at how to get input into our C code, and then finally, we're going to look at how we can have a heap of memory, how we can dynamically allocate memory for ourselves and why that's important. We'll look a little bit at the standard libraries. And then at the tail end of today's lecture, I also want to show how we can separate our files across multiple systems. So let's start by looking at this concept of how pointers and arrays are fundamentally very similar. We can, in fact, use a pointer to iterate through a set of elements, much like how we might use an array. Let me open up our source code. I'm going to do that using Vim. So Vim is a built-in code editor, much like Nano or Emacs. And so I have pre-configured my Vim to give me a little bit of syntax highlighting. So here we're going to go to 29 pointers arithmetic. I'm going to open this up. And here we can see my source code. And it's beautifully displayed in all sorts of colors the way you'd expect it to in any kind of code editor. Okay, so inside of here, you can see I'm going to include my standard input output because we're going to print things to our console. I have my main function. Inside my main function, really the driver here is to tie the concept of arrays to that of pointers. So the first thing I'm going to do is I'm going to create an array literal, and I'm going to save that into this array that holds 5 elements. I'm going to store that into this integer array. Then what I'm going to do is R is effectively a pointer to an array. It's a pointer to a contiguous block of memory in our source code. And so we could think of R as being at index 0. So in fact, when I grab R, I can also assign it as a integer pointer where we're pointing at the very first element. So effectively, this pointer is serving the same role as what our array is doing for us. They're both references to memory, to a block of memory, effectively. And so to prove this point, what we're going to do is we're going to iterate through both of them. So here I'm going to create a for loop, and then I'm going to use the box notation for each index value. So starting at index 0, and until I get to index 4, so all the way into the length of my array, I will index in, I will grab the element, and then I'm going to display that to the screen where I will show what the index value is and what is the element at that index. Then to illustrate that we can do the exact same concept inside of utilizing pointers, we're going to produce another for loop that looks exactly the same. And here we're going to dereference the pointer. Now, if we just dereference the pointer itself, that's going to be at index 0. So notice I can do what's called pointer arithmetic. And so arithmetic with pointers, since it's a memory address, works slightly different than the way that it works with integer numbers. With integers, whatever this value is, it adds to the other integer value, right? That's how addition works. But for pointer arithmetic, it's going to act as the indexer term. And so it takes into account the byte size of what it's pointing to. So for instance, since integers are 4 bytes, if we do pointer arithmetic starting at where the pointer is currently pointing at, and we add, say for instance, 0, then it's going to return back the same memory address. If we add 1, then it's going to advance our pointer by 4 bytes of space, because an integer encodes 4 bytes of it. So it's going to advance to the next legal addressable position that's not consumed by this particular data type. So in fact, what's happening here is each time we add index 1, it's moving our memory address by 4 bytes, and then 4 bytes again, and then 4 bytes again, which is where the starting value of the second value element would be, and the third element and the fourth element. So here we're using the indexer in a similar way. We'll offset that address, which is the address of index 0, and then we're going to use the star operator to dereference that. And once I have dereferenced that, I'll be able to grab that element, and then I can print that out the same that I did before. Now, once I've done that, I want to illustrate that I not only can read from arrays using either pointer arithmetic or pointers as well as arrays, but I can also write into an array. So using box notation, you can see here I can just index into element, this would be element 3, right? But at index 2, and assign that the value of 60, or I can dereference the value at and access the value at the pointer, and then use the pointer arithmetic to offset that by 3, right? So starting at 0, so this would actually be the fourth element, 0, 1, 2, 3, and then I will go ahead and save, or I'll overwrite the value there to 80. So now when we go and reprint out our array, and so while I'll iterate and index through each array using the box notation, we should see one of the values will be 60, the third value in there should be 60, and the fourth value should be 80 after we do these mutations. Let me use the terminal now to go ahead and actually compile our code so we can see this in practice. So let's call this pointers. We will run that. Okay, now let's run this, and we can see here inside my array notation, I am indexing, and I can see, yep, I'm accessing my values 10 through 50, which, remember, that is from my array literal that I had initialized. Then I can use the pointer notation to access those same set of elements. And then finally, you could see that the third element, the one at index 2, has been overridden to 60. And the fourth element, the one at index 3, has been overridden to 80. So I just wanted to go ahead and ensure that everyone had a strong understanding that we could do a one-to-one mapping with our arrays and our pointers. They can do similar behaviors for us. And the big difference here is notationally. Box notation versus this star notation that we use. Okay, excellent. Now, to exit out of my source code, I'm going to, in order for using Vim, I can hit the colon, which allows me to put in an instruction to the editor itself. I want to do :Q, which is the instruction to quit out. And then I will hit enter, and then it should bring me back to my terminal, and we will excellent. Okay, so the next thing I want to cover is I want to go more in depth with strings. Strings are an interesting thing. Let me open this up. Strings are interesting as they're not built into C. They're character pointers. So there's a lot of basic things we want to learn how to do with strings, and we have to learn how to use the tools that are available to us. So one of the advantages that Java has is it has a lot of built-in functionality for you with strings. We're going to see we do have options to access some standard library calls so that we can get more functionality with strings. It's such a fundamental concept for computing in general. So let's take a look at some of the basics related to strings. Here I have my, let me clear out this other tab here. Okay, so here I have my main function, and inside my main function, I'm going to show you two different ways that we can go ahead and create and store a string. One of these is going to be using the box notation, so as in a character array. And so recall, when we create a character array, we should reserve some amount of space that our string can consume in memory. And the alternate approach is we create a character pointer, and a character pointer can just be assigned this string literal. And of course, you don't define a block size for a pointer, but pointers can be really, they could be dangerous in the fact that they allow for overflow. So in this instance, when you're creating this memory address, it can just overwrite whatever is going to be in that block. So it's preferable to create a block size and reserve that for your strings over just having like an arbitrary size, since it's not actually reserved for your text. And then you can override important values because C allows you to do that. Very dangerous language, as we know. Okay, so once we have set these string variables, we can go ahead and print them. And we print them very similar to the way we might do that in Java. Okay, now if we want to override strings, if we're using the array notation, I can go ahead and do it very similar to any other imputation inside of a array. So I can use an index value. So I can access the first character at index 0 and change it to the character of F. And notice I'm using character notation there. It's a single quotes. And then at index 1, it would be O. At index 2, it would be O. And the important thing is, when you're done, you have to alert the system that the string is terminated using a null terminator character. The null terminator character is the escape code and then a 0 value. Alternatively, if we're using the pointer, we can just go ahead and reassign to a whole other string literal, right? We're just binding some new value into memory of that memory address. Of course, this is dangerous because it could potentially overwrite something that overwrite something behind it because of how much larger it is. But you could see how we can at least access this. Now let's actually run this. So I'm going to do GCC. And so first we will compile. This is our source code 30. And so let's call this now strings. Oops, no, not .i. Oh, here we go. Let's clear that. Okay, let's actually run our strings. And here we can see our string Binky, our string hello world, we have our foo, and then finally Ted was here and left this long message. Excellent. Okay, so that's the basics with strings. Let me exit out of here and let's look at some more nuanced things related to strings. So I'm going to open up concatenation, which is a very common thing you might want to do with two strings. Well, so the plus operator you can't use by default to concatenate. We actually have to now include our string library or our string header file, which will include the string functions that will allow us to do some interesting things with strings. And so we're going to start exploring that. So here, since it's part of the standard library, I can just include it using the angle bracket notation. Inside my main function, I'm just going to create a string that is hello. I'll create another string that is world. And of course, since this is a string literal, notice that it is optional to go ahead and define the block size, but then it reserves a block size that is the size of the string literal and not necessarily what the full size of the string is. So if your string's designed to be overridden so that it can have more than a set amount of characters, then you want to define a block size. Here, since we're going to use concatenation, we don't define a block size because it's only going to be used to concatenate onto string 1. So then I'm going to do string cat. And so when I do string cat, it's going to take the second string and it's going to concatenate it to the first string. And so it's going to actually mutate the state of the first string, the left parameter. So when I print this out, it's actually going to print hello world. And we can actually see this. Let's actually go ahead and compile our code and see this in practice. So here, this is 31. And let's call this also strings. There we go. And there we go. And so we can see the output is going to be hello world exactly as we would expect. Now to exit out my Vim, :Q. Oops. :Q. Okay, perfect. Now let's move on to the next concept related to strings, which is going to be how we can do string comparisons. So again, if we want to compare strings for equality, we can't use the excuse me, we can't use the double equal. So what we're going to do is we're going to import the string header file. That's going to give us many functions related to strings. Here, I'm going to create two strings to evaluate hello and world, str1 and str2. Then I'm going to go ahead and call strcmp, short for string compare. I'm going to pass it my two strings that I want to compare, and it's going to give me either a 0 for false or a non-zero value for true. So I can go ahead and then do a Boolean expression. If the result is equal to 0, then we can say the strings are equal. Otherwise, we could say it's, it's going to tell us the amount of difference between these two strings. So if the difference between the strings is 0, that means they're the same. And so here we will print out strings are equal. If there is any difference, so if it's a non-zero value, that means it actually returns a false value. And so then we know that these strings are not equal. So yes, that's that one thing you should be mindful of string compares. It's checking the difference between the two strings, and that's what it's going to be reporting back as a numerical value. So let's actually go ahead and test this. So GCC. And so here, let us do, what is this? This is 32. Perfect. -O. And then let's call this strings. And then what we can do here is just run strings. And here we see the strings are not equal. Pretty obvious. Okay. I'll clear out my terminal there. And let's close out of here. Okay, so next thing I want to look at with strings, going to be my source code 33 file. It's going to be the length of the string. So often is the time you want to know how long, how many characters is a string. So again, we can lean into the string library set of functions that we have. strlen, short for string length, we could pass a string into, and it's going to return back an integer value that represents the length of that string. So let's just do a quick test of this. GCC, this is 33. And let's call this application strings. And let's run our strings. Perfect. And we can see the length of hello world is, and then it gives us our length value right here. Excellent. So you can see many of the very common things that we'd want to do with strings, we have the ability to do through our standard library calls. And this is illustrating, first of all, how to use strings in a very powerful way, but another, why the standard library is such an important thing for you to look over for any kinds of tasks that are already kind of well-defined and provided for you to make your job as a developer that much easier. Okay, another very common thing that you might want to do with strings that's given to us in this strings library is going to be the ability to get a substring. So for instance, here, we have our string hello world. We can do the str, the string, which will give us the substring of, right here. It's going to see if it finds that substring, see that substring is contained within inside our larger string. So we're going to provide as the first parameter the string we want to evaluate. And as the second parameter, we're going to provide the string we want to see is a member of our main string. So is this a substring of the core string, the main string? And then so if this returns back a null value, then it did not find a substring. And if it returns a non-null value, then it did. And so what it will be returned is going to be, well, let's see here. Let's clear this. Let's run our code, GCC 34. And let's call this again strings. Here, we can see right there that what it's going to return is going to be, in fact, the substring that it was able to identify. And it's important to note that this substring that it's identifying is a character pointer, right? So it's actually pointing to that location inside the string where it identified. Okay, let's go ahead and put out of there. Let's move on to the next source code example. So inside this source code example, I am going to see how can we copy a string. So just kind of walking through this code, you can see that I'm going to create a source string with the string literal hello, save it to source. I'm going to create declare a character array. Both of these are character arrays. I'm going to create another character array called destination or dest that has a block size of 100, character size of 100. I can call string copy, strcpy. I give it as my first argument a destination, which is the thing I want to copy to. And then as a second argument, the source, the thing I'm copying from. And then what this should do is my destination should now have a copy of what was inside of my source string. So if I print that out, we should see that this should now say hello. Let's actually test this out to make sure it works. So let's do 35 dot strings dash copy string. Let's go to output. Let's call our application strings. And here we go. And we could see, in fact, we had copied the string hello. Okay, let's go ahead and exit out of here. Let's quit, quit. Okay, the next thing I want to do then is let's go and look at our source code, our example 36, where we'll look at strings some more, but for casting operations. Often is the case, actually, when we get input from the user, right, from the keyboard, it's actually just a collection of characters. And many times we are going to want to use this collection of characters in a meaningful way, such as to translate them or cast them into numerical representations, either as integers or floats or whatnot. And so here we can see using, notice here, we're going to use the standard library, stdlib, when we include on here, we're going to use that in order to be able to translate between our set of characters into into our integers or floating point values. So that's how we're going to do our casting operations. So let's see how we can do this. The first thing we're going to do is we're going to create a character array. That's going to be a string of well, it's a string of numbers, 1, 2, 3, but characters. And then here we're going to have a character array that will be a string that kind of represents a floating point value, but it's a string. So now the next thing we want to do is we want to translate our string, cast our string into an integer value. We can do that with a to I. So it's effectively ASCII to integer. And then we can pass it our integer string, and then it's going to return back to us. It's going to try to parse that into an integer value. And then I could also do A to F. That's going to be ASCII to float. I can pass it that string that has a float value, and then it's going to return back to me a double float value. And so here I can then print these up, and notice when I print these up, I'll be able to actually use the %d to print an integer value and the %f to print a floating point value. I'm not actually printing the strings, the %s. Okay, let's actually evaluate this. Let's actually run this and see what the output looks like. So this is going to be 36 dash strings Cassie, and I'm going to call my application strings. Let's execute that. So that compiled. So now let's execute it. And we can see, yep, my integer value is 123. And my floating point value is 123.45. Okay, so let me clear out here. And let me go back over here. Okay, and now the next thing I'm going to do is we're going to move on from looking at strings and actually examine a little bit deeper the concept of functions. So source code example 37, we'll look in particular at some function prototypes. So the function prototype is, okay, going to come before our main function. So any time you want to call a function, you should have the prototype defined before it's invoked and so a prototype can also be its definition as well. So I want to articulate this, and I don't have to put a prototype here if I were to define the function where the prototype is currently at. So this is the prototype. The prototype effectively in Java looks like what a abstract method might look like. Effectively, it has a return type, it has the function name, and it has the set of parameters. And this alerts effectively the C compiler that when it sees this function call, that in order for it to be valid and legal, it requires this inputs, and it will return this output. Now, provided the compiler has this information, now we know when we go to compile the main function, whether that function is used properly or not, so that we can go ahead and compile that. So notice in main function, we haven't defined this yet. We've simply declared it. The definition of it is after our main function, where I go ahead and actually give that function a body. So inside my main function, I'm just going to go ahead and create two variables, a and a b. I'm going to create, and I'm going to set those with the values respectively of 5 and 10. I'm going to declare a value for sum. And then what I'm going to do is I'm going to invoke add, which I have the prototype here and the definition here underneath our main function. So we can see, just looking at the definition of our main function, it's going to take those two parameters, num1 and num2. It's going to add them together, and it's going to return it. So here I'm going to invoke, or call that add function. I'm going to pass it my two parameters. It's going to return back to me a value, and then I'm going to print the result of that value, that sum. And so again, the big takeaway here is we can go ahead and declare functions before defining them at the top of our code. Then we can actually use them inside of something like the main function. And then underneath them, we can go underneath and actually create the definitions for them. Now, as I stated earlier, I could create the definitions here, and then I would need the prototype. But the idea behind the prototypes is we're going to see in this lecture a little bit in a couple future examples, is that we want to actually put all of our prototypes in a separate file called header file, which actually has the extension .h, which you might notice is what we constantly include and import into our source code files. So by convention, that's where we typically want to put all of our prototypes. And the prototypes, in a way, that's our API to our other end users. It's what's publicly available from our source code files, so other source code files can go ahead and use. And so we'll take a look at some other examples that kind of motivate how functions use in a moment. Let's actually test this though. We haven't done that yet. So let's go to GCC, and then this is example 37. And inside of example 37, I'm going to go ahead and let's do this. Let's call this func in terms of our app name. And so let's run our func. And there we can see it runs as we probably expect it should. Okay, now let's move on to example 38. So in example 38, I really want to compare the concept of passing by reference versus passing by value. Since we do have this concept of memory addresses, as we talked about earlier, and we have accessibility from those using pointers and then also the star operator and also the ampersand operator, the address operator. Let's see how this actually has some consequences, how we can make use of this in terms of implementing our functions. So here, let's take a look at these two function prototypes that we're looking at. The first one has a return type of void, and that's because we're going to add by reference. So we don't have to return something. We're going to mutate the state of the value that gets passed to us. So notice here, the first parameter is going to be a pointer to an integer. So we're going to give it the address of a variable, some integer variable that we already have. And then we're going to actually pass it a value. So this isn't a pointer, this is a value of some other value. And then we're going to go ahead and compare and contrast that to this other function. The prototype for is here, add by value. Notice the two parameters here are both values. They're not pointers. So you're actually going to put in numerical values here. It's actually going to return back the integer. Okay, so let's see how we can use these to produce similar results, but in very different ways. I'm going to create a variable inside my main function called original value. I'm going to create another value called 5, which is what I'm going to probably add to my original value. Here, my original value will print out. Then here, I'm going to call my add by reference, and this is void. So what I'm doing is I'm giving it the address. So I'm going to use the ampersand operator to give it the address of my variable, of where my variable is in memory, original value, which is where my 10 is stored at. And I'm going to pass the value of other value, that's 5. So what we can see, let's jump to the source code to see what's going to happen here. So coming down here to line 26, we can say I'm going to use the star operator to dereference the value that's in that memory address, and I'm then going to add to it, I'm going to use the compounds assignment to add to it and overwrite it with the value of other. And so now it's going to mutate the state of 10 to now be 15 inside that same memory address. So now anything that had a reference to original value here will now have that changed state. And now I'm going to actually print original value from the scope of the main function. Okay, let's look at this again. I have my original value. I'm going to overwrite it back to 10 so that we can do this again. I'm going to print my original value to the display. I will then go ahead and then add by value. So here I'm actually just passing in the numerical value. So this would be 10 and 5. And now this is going to return back a value, which I can then assign to original value and then go ahead and show original value this way. So both these blocks here, this one and this one, are effectively doing the same thing. It's just one is a function that passes by reference and then goes ahead and overwrites the original variable inside of that function. The other passes by a value, and it requires you to do the assignment from what gets returned. Clearly, one can be way more dangerous than the other in terms of affecting code in places that you might not expect it. Okay, let's actually run this. So this is my example 38, and let's call this func, because we're looking at functions. And so let's run our func app, and here we see our original value is 10. After our add by reference, it's 15. Our original value is 10. After our modify by value, it is 15, just as we'd expect. Okay. Sorry about that. Little wake-up call in case you fell asleep. Okay, so the next thing I want to look at is going to be example 39, which is going to be a basic common use case on why we might want to implement by passing by reference versus passing by value. Because we know passing by reference can potentially be dangerous, but sometimes it's very necessary. So on these very common instances where you need to swap the positions of two things in memory, such as like if you're sorting something, then we want to do that using the passing by reference. And so here, let's just take a look. Here's an example where I wanted to do an example also that doesn't use a prototype, that does our function definition at the top, which means we don't have to include a prototype. Now, I think we have seen this a couple times in our earlier examples too, before we introduced functions. So let's take a look at this function definition. We have our pointer, two integer pointers, x and y. And so here we will dereference the value at x and hold that actual value in some temporary variable inside of this function. Then we will take the value from dereferencing y and overwrite that into x. Then we'll take that value of that we are storing in local variable and overwrite the y value. So now this allows us to switch the values between two sets of variables, or two positions inside of an array if we were using this to sort. So suppose here then in my main function, I have my variables a and b. Here I will print out what the values are before I swap them. Then here I will swap them. And since this is looking for memory addresses, I'm going to use the ampersand operator. So I give it the address of those variables. And then I will then print out a and b after swapping, and they should in fact be swapped. And in fact, we will test that. So let us go ahead and compile our code. Let's name it something useful. I'm going to stick with func, and let's run our func code. There we go. And we can see, yeah, before we swap them, our values were a is equal to 1 and b is equal to 2. And after swapping, a is equal to 2 and b is equal to 1. So that's one motivation as to why we might want to use passing by reference. So when it's very common to use. Okay. The next thing I want to discuss is going to be the constant keyword inside of C. So constant allows us to ensure that when we have our source code, if we're passing a value, that it can't be overridden, because clearly we can see it's that's a very dangerous thing that can occur. And so if we want to protect against that, but still pass by reference, we can add here the keyword inside of our parameter list const. And so this will make a constant integer pointer. And so let's look at what the expected behavior is going to be here. Let's look at our function definition. So in our function definition here, so this was our prototype, right? So let's go to the definition itself. So here we're going to print the pointer. We're going to dereference the pointer and print the value there. And so if I tried then to dereference the pointer and overwrite that value, this would actually cause a compile error, because this was given to us as a constant. So it prevents us from being able to overwrite it. And so here inside of our main function, I'm going to create a variable, a number 10. I'm going to give it the memory address, right? I'm going to use the ampersand operator to give the address of that variable. And I'm going to send that to that function, and this will work. And then what we're going to do is we're going to uncomment this out and see how it breaks for us. So let's first run it with everything commented out and ensure our code works the way we expect it to. So let's do, this is, we're still in func. Yeah, we're still in func. So let's run that, and that runs per normal. Okay, so now I want to make a change to my source code file. If I want to make a change to my source code file inside of Vim, I have to go into insert mode. If I want to do insert mode, I will hit I. And so now I allows me, you can see I now have a cursor. And actually, if you look at the very bottom of my screen, it now shows me what mode I'm in, which is insert mode. So now I can go ahead and toggle to the line that I want to modify, and then just modify it. So I will remove those two slashes. So now this is not a commented line. Now, when I want to exit insert mode and then get back into like my main mode of Vim, I would hit the escape. And now notice in the bottom, it no longer says insert. And then I would do colon, and I don't want to just do Q here because that just quits me. I want to actually write this change to the file. So I will do W, which means write, and then can follow that with Q. So we'll write the change and then quit. And so now that allows me to come out here. And so let us recompile our code. And so now when we try recompile, we see, oh, I can't do that because that's a read-only variable and it's not assignable. And so that's, if we want to kind of include guaranteed protections when we use pass by reference, that's how we can do that. Okay, let us actually go back in there and recomment that out. So the next time when I save this with you, it'll be fine. So again, I'll enter insert mode by hitting I. I'll add back these / to comment out my code. Now I will exit out of insert mode using escape. I will use :WQ to write and quit. Perfect. Okay, now let's go to Vim. Let's go to our example 41, which is going to be static functions. So in C, a static function has the file scope, which means it can only be called from the same source code file. So whenever we declare a function as static, it's a way for us to implement with encapsulation. That's our mechanism in C to encapsulate things, which provides a form of information hiding at the file level. So any static functions can only be called from this source code file. Anything that's non-static, on the other hand, can be externally linked to some other source code file, which means that we can hashtag include them from another file. And we'll look at how to do that later on. So functions that are designed to be publicly available so that other source code files can access them, we would just leave them as non-static files. Now, if you have a helper function, or if you have functions that are just specific to this application, to this source code file, and you don't want them to be publicly available, then you should define those as static. And just to highlight that, here, let's take a look at the source code file. I have this one prototype. It's just return type void. It's called non-static function. Here I have a static function declaration, a definition, where I'm going to just print static function inside static function. And then here, this is my non-static function definition, where it's just going to print inside non-static function. And then here inside of my main function, we can see all we're going to do inside my main function is I'm going to invoke my non-static function. I'm going to invoke my static function, which is going to print those things. And let's take a look at it just so we can see. First, I'm going to clear my terminal. Okay, so let's do GC. Then we could do, what is that? That's 41. Yeah, and then let's call this func, because we're still inside of functions. And now there we go. Perfect. Calling non-static function inside a non-static function, calling static function. Now we're inside a static function. But really, the big takeaway for those is whether you want that function to be available outside the source code file, which is going to indicate whether you should declare it as static or not. Okay, let's quit out of that. Okay, let's move on to example 42. And so example 42 is going to be a really interesting example. It's one that I included because you are all Java developers, and I had a really interesting question. This is about function pointers. So someone had asked me about structs. When we were talking about structs, we can go ahead and we can embed data in there, very similar to how an object is. And then someone's like, but can you go ahead and define a function? And I'm like, and I answered in a way that alluded, yes, you can, but it's not the same kind of syntax that you might expect inside of Java. So the idea is that everything inside of our system has a memory address, including our own source code. And so if you think about what a pointer is just it points to some location in memory. And so a lot of times the things that we have in memory, they're either values, or the way that we think of them is as a value or as a set of instructions, as a function. But the function itself is inside of memory so that it can be invoked. So we can actually create a structure that has a pointer to a function. And in fact, if you want to know how C was built on top of C. That's one of the concepts that that made use of that, is that you can go ahead and create things very similar to objects that include fields that have properties and also have methods that have functions that relate to those to that particular structure in and of itself using these function pointers. So let's see how this actually looks in practice. The first thing I'm going to do, I'm going to create a type def structure called fraction. And so here, let's define what our fraction is. It's going to have a numerator. It's going to have a denominator, and both those are going to hold integer values. And then notice these are my function pointer declarations. So a function pointer declaration kind of merges two different aesthetics, if you think about it. It kind of looks like a prototype in one regard, but it also looks like a pointer in another regard. So if you took the concept of a pointer and merged it with a prototype, that's effectively how we declare our function pointers. So that what that means is, in order to have a function pointer, we have to provide what is the return type. We have to define what is the name of the function, and now we preface the function name using a star operator to illustrate that we're going to use the memory address of that named function. And then here, we're going to go ahead and have a parameter list that function uses. And so this is what I mean when I say this is kind of like a prototype of sorts, because it gives us the return type, it gives us the name, and it gives us the parameter list. However, it's not a prototype, it's a pointer to a function, because we're going to prepend it with that star operator. And so we'll do the same thing here. So this is an init function that we're going to declare a pointer for, and then we're also going to declare a pointer for a print function. It's going to return back also a void. It's going to have a fraction that passes into it, and the actual function name will be print. And since this will be a pointer to this function, we will again use the star operator to illustrate that this is a function pointer. So now let's actually define two functions in memory so that these can be pointed to. So here I will have a function init fraction, right? I will declare this and define it just like a standard function. So return type void, it's going to match my parameter list, and then it's going to have this name. And again, the name that we're using here, this is a pointer. The name we're using here does not have to match this name, right? This is the name that we're giving inside of our structure, because I'm going to be able to assign that. So here I'll actually create a function init fraction, and this is something that now is inside of memory, right? This is now something that's well defined, and I can access that using that name just like a variable. So recall I invoke a function using a set of parentheses. That's how I call it, but I can access its memory address by just using its name, kind of like how I can do that with an array. So a function's name is very much kind of like a pointer to where that block of code is in memory. Okay, so now, so we have this implementation. What this implementation is doing is it's going to take a pointer to a fraction. It'll take a integer value for numerator, an integer value for denominator, and it will dereference, it'll access using the arrow operators, the field for numerator and denominator, and set those. Let's take a look at our print fraction function. Here, we're going to take in a fraction and make sure it's constant so you can't override it, because we just want to have read-only privileges on it. We're going to use those arrow operators to access the numerator and denominator values, and we're going to print that out. Okay, so now the idea is we want to bind this print fraction and this init fraction to these function pointers, init and print. So let's go into our main function and see how we can do that. I'm going to create two fraction variables, f1 and f2. On f1, it's going to have a property init, which is our function pointer, and I can just assign to it init fraction. And now notice I'm not invoking that function. I'm just giving it the name, which is the memory address to that block of code. And so here I can do the same thing to set onto f1 print that print fraction function to the print function on on our structure. And then I'll do the same thing here. I'll go ahead and do the same thing for F2. I will bind those functions to my F2 under init print and F2 init and F2 print. And now what I'm going to do is on F1 and F2, I'm going to invoke the functions on it. I'm going to pass the memory address using the ampersand operator of that actual of itself. So if you want to think about what this is, that's kind of what this keyword in Java is doing. So this is going to be the memory address of this data structure, and I'm going to pass the values of 1 and 2 so we can initialize this fraction. And I'm going to do the same thing here on F2, this particular fraction struct. I'm going to pass its memory address to that init function with 3 and 4. And then I'm going to go ahead and tell F1 to print using its own memory address and F2 to print with its own memory address. Okay, now that we've kind of explained function pointers a little bit, hopefully it's not too confusing. Let's go ahead and actually test them out. And here we can see our fraction 1 will print out as 1/2, and our fraction 2 will print out as 3/4, exactly as we should expect it to. Excellent. Okay, let's clear this out. And let's quit from there. Okay, I want to move on to my next example. So let's move to example 43. And so this will be our input numbers. So far we've looked at how to output things into the console, but we haven't really examined deeply how can we get user input from the keyboard and get that into our software. And so we should take a look at that. So in order to do this, first of all, I'm going to go ahead and grab I'm going to use standard input output clearly for the input operation, but for this particular basic code, the sample code, what we want to do is numbers. I don't think I actually need this here, actually. So I'm going to go into insert mode. What I'm going to do here is I'm going to remove this need for string, because the first types of inputs I want to examine are going to be, let's write that. Okay. The first set of examples that I want to show off are going to be how do we get numbers from the end user. So let's take a look at our main function here. We're going to create a variable to hold an int value. We're going to create a variable to hold a float value. I'm just going to create a buffer that can hold 100 characters. Now I'm going to create a prompt, enter an integer. So I'm going to print f that. And so if I want to grab data from the input stream, from the system input stream, I can use scanf. That's a built-in function. So if you wondered where the term scanner came from Java, again, it borrows a lot of its terminology from C. So scanf, and notice with scanf, I'm going to go ahead and give it a reference to my int value. And I can, when I do that, I can also give it it's a formatted scan, so I can give it a formatted string as well. So here it's going to be an integer value, so %d should allow for me to be able to parse that. Okay, and then here I will go ahead and prompt the user enter a float. Again, I'll give the formatting instructions. The %f illustrates floating point value. And then here, I'm going to give the memory address of my variable to hold my floating point value. And again, the %d allows it to parse that character and let it know, treat this as an integer, and it will then bind that to this space in memory that is at the address of int value. Same thing, same concept, but with a floating point value here. Then after we're done, you should always go through, call get character, and just continue to consume whatever's inside of your input stream that is new line characters, because that can really dirty and muck things up. So this is just a good way of cleaning out your buffer. And then we will go ahead and then print these states. Okay, let's do GCC. And let's actually, this is 43. And let's actually call this inputs, because now we're in a new section. And let's run our inputs application. And there it is. Enter an integer. Let's enter 1, 2, 3, 4, 5. And enter a float 3.14159. Excellent. And you can see integer 1, 2, 3, 4, 5. And our float is 3.14159. Excellent. That's exactly what we want. So let me clear this. Okay, so that's one way that we can go ahead and access numbers, right, from our input stream. Let's see how we can get strings. Strings can be actually a little bit more complicated from numbers for a variety of reasons, and that's because of how difficult it is to know how we should parse these strings. Okay. So we're going to look at 3 different ways to parse a string. We're going to look at what seems to would appear on the surface to be the obvious way, but is actually the dangerous way that we want to avoid. Then we'll look at a safer way that's still the dangerous way and still not a great way. But we're going to look at it and then we're going to see the way we should do it, and the way that the safest way, and the way that after we examine this is how you should always go ahead and get strings from the input stream. Okay, so the first thing we're going to do here is, we're going to grab our standard input output clearly because we're doing input operations. Then we're also going to grab our string library of calls, because we're going to do some string modifications here. Inside my main function, I'm going to create a character array that can hold a block size of 10 for my string value. I'm going to create a prompt to the user to say, hey, enter a short string, and I'm going to let them know this is the dangerous way. Then I'm going to do what looked like what we were doing for our floats and for our integers. I'm going to call scanf. I'm going to give it, hey, we're looking for a string, so the format of what we're going to parse is going to be %s, and then the string value. And so again, since we're just doing %s, it's only going to parse that single string. So keep in mind that empty spaces, new line characters, tab characters, all are delimiters. So it'll cut off using this particular methodology. So you won't. So if I try to put a space in between the word, it'll treat the space as a cutoff point, as a demarcation for our strings for tokenization purposes. Okay, so this is dangerous because it doesn't set a limit specified. And so that's dangerous because, well, we know that the array size is only allocating 10 blocks of memory. But if I don't control this to make sure the thing that I'm reading into my string value is reserved at 10 things, then I can just go past that and it'll override an 11th, a 12th, a 13th, 100th, 1,000th, and all of a sudden you've lost all those values in memory, and now it has new values that you did not want. So it can cause erroneous behavior. That's what makes this very dangerous. So this is what we want to avoid, right? Because this allows for what are called buffer overflows of your memory space, which can cause you to destroy anything you have in storage by accident. And then we're going to do our clear our buffer. Then we're going to look at the safer way. The safer way is we're going to do the same thing, slightly safer, because when we do our scanf inside of our format statement, we could put a number between the % and the s, and that indicates how many characters it will parse before it stops. And so this will prevent a buffer overflow, but still not incredibly safe. Still not the way we want to go about it. There's still ways around this. And also, with this particular formatting, you have to know exactly how many things you're actually going to pull. This is going to force 9 characters regardless. But not just that, it doesn't support multiple words either with this particular formatting. So again, after we do this like safer way, but still not ideal way, we will then go ahead and clear out our input stream of any new line characters. And then we're going to do the safest way. The safest way is there's actually a function inside of our strings. There's actually a function inside of our standard library called fgets, and fgets allows us to pass in this array, right, the string value where we want to send this to in terms of the data in our application. And then we give it the size of some size. So we give it a numerical value. So size of is an operator in C that will check the size of string value, in terms of byte size. And then we will pass it as a third parameter, the standard input stream. And so what it'll effectively do is it'll grab that amount of bytes from the standard input and get it and place it into your string value, into our string value array. And then once we have that, what we'll do is we'll then use that this string CSPN to remove the new line character that's in there. So again, this is a function call that's part of our strings library so that we can sanitize our string so it's just the text itself and not the action of hitting the enter that the user had done. Okay, let's actually test this out. So the consequence of all this is you want to kind of use fgets whenever possible for grabbing strings because it's the safest way to grab it from system in. Now this is 44, excellent, -o. And so here, what I'm going to do is let's call this strings, no input, on inputs. And let's run our input. And there it is, enter a short string, Ted Holmberg was here. Okay, so first of all, we know that's going to cut off because I have, yep, Ted. So notice it cut off because of the formatting. Just %s uses that delimiter. That's what I was talking about before. And this is a safer way, but still it's going to do the same issue where it's going to cut off. Yep, it just says Ted, and then it cuts off after the space, so it delimits. And then Ted Berg was here. And so here, this will grab up until I run out of my buffer space. That's the safest way. Now let me run that one more time, but with a contiguous word. So Ted Holmberg was here. And see, entire thing, Ted Holmberg, which is dangerous. That cuts us off, so that's safer. And then finally, Ted Holmberg was here. Safest. Excellent. And it even lets us know when we violate it. When we violated our buffer size, as you saw. Okay, let's quit out of that and move on. So the next thing I want to do is go to example 45, where we can start moving on from some of these basic concepts and talk about one other kind of fundamental component that makes C so interesting. And one thing that Java has tried to improve upon C is the idea of dynamically allocating memory for you. So one of the dangerous things about, so notice every time we need to reserve space for ourselves, we've been doing it statically. Statically means that we specify ahead of time how many blocks of bytes we need to reserve in memory before we start storing values there. And of course, you don't always know what that is until runtime occurs. And so sometimes you want to have the ability to dynamically allocate the amount of space you need when you need it, and then free that up later on. So in Java, you might recall the concepts of like garbage collection. So when you create variables in Java, one thing the JVM does for you is it creates the memory blocks for you. And then as you dereference everything, it becomes a dangling reference. It doesn't exist any long, and then it gets reaped. It gets reabsorbed. It gets collected by the garbage collector and frees it up that memory so you can reuse it somewhere else. So this idea of dynamic memory allocation in Java was motivated for us from C, but it's something we have to manage manually. So we have to dynamically request from the heap of memory however much memory we want when we need it, and then we have to free it up when we're not using it any longer. Now, there's tons of reasons why you should use dynamic memory allocation, which is typically referred to as Malloc, short for memory allocation, to over statically allocated memory. And that's for a number of reasons. Flexibility, like we said before. It also, if you're using dynamic memory, you're going to avoid those buffer overflows because you're not just writing into like static memory addresses. It allows you to have immutable string literals. It's a more efficient use of your memory, and it just gives you better control over your data over the lifetime of your application. So with that said, let's see how we can actually just declare an integer value, something very simple, using Malloc, using a dynamic memory heap, as opposed to putting it in static memory. So the first thing you're going to see is I'm going to create a integer pointer. First of all, I need to include the standard library, which has the malloc and free functions in them, defined in them. So inside my main function, then I'm going to create this pointer to an integer. And this integer pointer is going to invoke so I'm going to invoke the malloc function, and I'm letting the malloc function know, hey, the type of data that I'm allocating my dynamic memory for is for integer type. So I need a integer pointer. And so the size of the memory then that I need to reserve in my dynamic memory is going to be what the size of an integer in bytes is. So size of is, again, an operator that lets us know how many bytes a particular data type consumes. And so then once I do this, this will create a memory address. So notice I'm assigning this. So this creates a memory address inside my memory heap that I can then bind as an integer pointer and set values into. And so when I set values here, it's no longer in my static memory address, it's in my dynamic memory address that I've now allocated that has a byte size of 4. So then I'm going to check to see if the pointer is not null, if it actually is a reference. If it is null, I'm going to say, oh yeah, my memory allocation failed. And I'm going to return out, and I'm going to return a non-zero value to say, hey, something happened that was bad with my application. Okay, so then I can start saving values inside my dynamic memory for this particular 4-byte storage size that I have. So I can use my star operator to dereference and access that space for values, and I will assign the value of 10. Then I will dereference the value that is stored in that memory and print that out. The value in the allocated memory is 10. And then when I'm done, the last thing I need to do, once I've allocated the memory, can never forget this, is then call the free function and provide it the pointer to that address so it can be reaped and reallocated back to the memory heap. And then it's sometimes good after that to then overwrite that pointer to ensure that it's now set to null and doesn't have that old memory address that's no longer valid any longer. So let's test this out. And let's call this heaps. And let's run our heaps application. And so here we can see value in the allocated memory is 10, exactly what we had expected to be. Okay, so let's look more at heaps, at other examples. So this was a very basic example where we kind of showed off how to use heap memory for just an integer. But more commonly, you're going to use it to store dynamically sized arrays and dynamically sized strings. So let's look at how we can use this for arrays. This is the same text that we had before. So let's just skip past that. Okay, so here we can see I have my, I'm going to include my standard input, output, and my standard library. Of course, I need standard library to be able to go ahead and be able to use my malloc and my free functions, and standard input output because we're actually going to use scanf and we're going to use some print statements. Okay, so the first thing I'm going to do, I'm going to declare an integer pointer for an array. which is going to be what we want to store in dynamic memory. So, so again, this is just a pointer. So that's going to be a memory address, right? So when we declare a memory address, the memory address is going to map to some place in our memory heap. Then I'm going to create a number of elements that we're going to query the user for effectively. Then I'm going to send a prompt to the user, hey, enter the number of elements. Here, I'm going to call scanf. I'm going to use as my formatting string %d because that's what I'm going to parse from my system input stream. And I'm going to bind that towards the address of number of elements. So then I get from the user the number of elements. Then what I'm going to do is I'm going to set up malloc. And so since the data type that is going to be held inside of this array is of an integer type, we need an integer pointer inside to be memory allocated for us. And the size of this integer, this set of memory addresses, so this pointer into memory for X amount of memory addresses is going to be the number of elements, right? So it's effectively going to be the account of our array size multiplied by the byte size that each of those elements are. So if, say, for instance, the number of elements is 10, and say, for instance, the size of an integer is 4, then we have to allocate 40 bytes of space and memory for this memory address, for our integer pointer, for our malloc dynamic heap of memory. Okay, so now we have set array, and so now this array points to our dynamic heap, to our as opposed to our as opposed to being statically typed. So this could have been whatever the user puts in, which normally we can't do. Normally, when we declare an array using the static typing, we have to say ahead of time if it's 10 or 20 or 1,000. But notice when we run this application, the size of this array can be whatever the user ends up inputting. And that illustrates the power of this particular availability of having a memory allocation to us. So then we'll do the safety thing. If the array's pointer is null, then we're going to exit out because it didn't work for some reason. And then what we're going to do is we're going to make a print statement to show, hey, this is the number of elements. Then we're going to create a for loop that indexes through the address of array, right? So we'll use the address, and then we can use the box notation to get that index, and then just keep printing all the elements from the user. Actually, what we're doing here, I'm sorry, I skipped ahead. I was thinking about printing here. What we're doing here is we're scanning. We're going to ask the user to type in X number of values to impute into the array. So if we knew that, so I said earlier, if the number of elements is 10, so starting at index 0, we're going to go use box notation and then use the address of to give access to the scanf, right? The ability to parse a integer value and then store that in memory that's been allocated to us from our memory heap. And so after this block of code, we're going to write values that the user gives to us into memory. And then in this block here, we're then going to print back and read those values from our dynamic memory. And then when we're done the application, we have to use that memory address and pass it to the free function so it can be reaped and harvested and reallocated. And then set that array pointer to null. Okay, let's take a look at how this looks in practice. Okay, heaps and heaps. And here we can see, enter the number of elements. I'm going to do 5. Okay, let's do 10, 20, 30, 40, 50. And here we see I entered 10, 20, 30, 40, 50. Excellent. So that is a very powerful concept related to being able to dynamically and flexibly respond as the application is actually running. So that's a much more memory efficient way of allocating space for our arrays. And actually, let's look at the same thing, but as it relates to our strings. So here we can see all the same basic concepts. This is still the same preamble as before. Let's take a look at this implementation. I'm going to create a character pointer that's going to represent a pointing to my dynamic string. I'm going to create a variable to hold the length of the string. Here, I'm going to prompt the user to illustrate how dynamic this is. In order to prove how dynamic it is, we want to do it while the application is running and not statically define these things. So here, we're going to use scanf to grab input from the user. We're going to parse the input from the system stream as from the input stream as an integer, and then we're going to provide the address of our variable here to be able to grab the length of our string. Okay, once we have the length of the string, we can allocate in memory the amount of space we need to store it. So here we're going to request for a character pointer from our from memory allocation that's going to be the length plus 1, so the number of characters plus 1 for the null terminator that follows, and we'll multiply that by the size of the byte size of what a character encodes at, which is just 1 byte. And then, so this should return to us a memory address. We'll check to make sure that the memory address is not null. If it is null, then we return out of the application with an error of 1, just some non-zero value, so we know, hey, this did not return correctly. Then we're going to go ahead and request for the user, hey, prompt the user enter string. Then we're going to do scanf again. We're going to pass it our dynamic string memory address, which is already a memory address, right? So I don't have to use the ampersand operator on that. And again, we're going to parse from the user %s. And so here we'll then show how we had grabbed this from the user. And we're just doing a simple way, proof of concept. And then finally, what we're going to do here is we will free that memory address once we're done using it, and then we'll set the pointer that originally referenced it to null. And so here, let's make sure our code works. And this is heaps. And here we can see enter the maximum length of your string. Well, let's say that my string will be called, let's say it is 6. Now let's do just 3. Enter the string tab. You entered Ted. Excellent. And of course, I could have entered any number of values and it would dynamically grow to be however big I need that string to be. Let's clear that. Okay, so that's some example of how we can use Malloc and how we use free to be able to dynamically allocate memory for things that can potentially vary when our application runs. So that's how we handle those things in C. So there's just a couple more things I want to show off in today's lecture. One common thing that you're familiar with in Java is having a lot of standard libraries that enrich functionality, like say, for instance, with math. So you have your basic mathematical operations like plus and minus and division and multiplication. But if you wanted to do more complex mathematics, the standard library includes things like that. And so I would advocate you all to go and read the actual libraries, the actual documentation on the libraries. But to give you an example of what you can do, we can include, say, for instance, the math functions, the math library, and that will give us the ability to do like square roots and to be able to take the power where I give the number and the exponent value. So we can bring something from number and base, a log 10 or just a logarithmic value. I can take pi here, which is defined for me when I import this. I can take sine or cosine. I can take absolute value. So pretty much any kind of thing, and so this is going to be fractional absolute value. It supports floating point number. So here you could see many of the mathematical operations that you would that you could utilize from the math package of Java. They have a math library for you here in C. I'm not even going to bother. Well, yeah, I might as well. GCC 48-0, and let's just call this math, and let's run our maths app. Excellent. You can see we can easily run all those calls. Okay, the last thing that I want to do for today's lecture is show you how we can split our code into multiple files. So let me start by showing you this one. So we'll look at, so how can I use, so really the motivation is we've been including these header files, these hashtag include and then some file name .h. So I want to show you how we can do that, how we can make our own header files and how you can import header files that you author yourself or that other people author into your applications. So let's take a look at, first of all, the header file. So, oops, this is 49. So here, let's do .h. Okay, so here, when I define a header file, really by convention, all we put in there are our function prototypes. So I'm going to create a function prototype, and a function prototype is just the return type, the name of the function, and the inputs that it requires. So here, this is going to return nothing. It's going to be called bar. It doesn't take any inputs. Pretty simple. Okay, let's actually define that function. So now I'm going to go into, typically, when I define those functions here, I'm going to go into my C file. And so if I want to define that function, I have to include the header file for it. So notice the first thing I'm doing here is I'm going to include 49, example 49 multi-c files.h. So this is going to include from here my local directory. It's going to look at my local directory, see if I have a file like that, and then it's going to include that when I go to compile my code. And then I'm also going to include my standard input header so I can get the print. So now I'm actually going to define that function. So void bar, and since it's a non-static function, I can import it into another application, which is what I'm going to do. And then here it's just going to print hello world. It's pretty simple function. So here I'm just defining it. But I don't have to have the prototype because the prototype is now included in the header file. So now what I want to do is I want to actually show you another the main where my main function is. So I can have some other source code file here, and then all I have to do is include the header file. So hashtag include, and in this instance, it's called 49 multi c files.h, which has the prototype. And now because I have that prototype, I can have a main function that now invokes it. And now I'll grab that implementation that is part of that got defined inside of the C file. Now, the trick is when I go to compile this, I have to compile both of my C files. So let's do GCC. Let's do 49 .c. And then let's also do my main, right? Perfect. And let's call this multi files. Multi, I'll just call it multi. And then let's run our multi. And here you could see I can now run this code, hello world, just like normal. So I just wanted to give you a visual example of how we can start subdividing our code base amongst multiple C files and then how we can include them in one another by defining our prototypes in these header files and then including our header files into our C files and compiling it. And during the compilation process, it links all this code together for us, which we'll talk about later. Okay, we talked about a lot, and we got to the very end of our overview on C. The next lecture, probably what I'll do is I will show a capstone project, or maybe I might make a bonus lecture where I'll show a capstone of a to-do application that's written in C, so you can see all these kind of disjointed pieces come together to actually build a kind of basic application, kind of the kind of application that most people do as their first entry into a language, a to-do application. So I'll challenge you first and foremost, see if you can't design your own to-do application. And then next time we come together, what would be great is to see what roadblocks you've gotten yourself into and see if your implementation matches that of my simple implementation. So just so you know, the implementation I'm going to show off will include just 4 features. One will be able to add a to-do item. One will be able to read your to-do list. The other will be to delete a to-do item. And the fourth and final feature is to exit the application. So see if you can't build a C application after watching all of these lectures and going through all this source code that is simple like that. And then what we'll do is we'll actually walk through it in class together and see what hangups you've had. This is a good opportunity to see and challenge how much of this C knowledge you're actually grasping. Okay, with that said, I am done with this lecture. I am happy with where we're at. I will see you all next class. Have a great day.